Is up, happy peoples? This is G Soul, and today we're going to talk about the chi-square goodness of fit test. Um, as you see, this central question, we want to talk about how the chi-square goodness of fit test helps to determine if a distribution shows that it's a significant change in the entire distribution breakdown from what is expected. So, the chi-square goodness of test is going to involve a couple things. First of all, making sure that we have a list of values, and we're going to talk about how different our observed counts from differ from our expected counts. So we want to keep that in mind as we go through and look at this here. We're going to start off by talking about M&Ms again. I don't have real M&Ms for us, but we're going to talk about um, M&Ms because M&Ms are fun and chocolatey and fun. All right, so we want to look at this here. We have according to information provided by Mars, the distribution of plain milk chocolate M&M should be approximately blue 24%, orange 20, green 16, yellow 14, red 13, and brown 13. And a bag of M&M shows the following distribution as such. And I want to remind us that if we need to stop in order to record this information, let's do so. I'm going to proceed for right now. But again, as we're watching this, if we need to stop, please pause the video so that you can record the information that is needed so that we can continue. All right? All right. So one type of question that we could answer is if we look at individual colors, are the distribution of those particular individual colors significantly different than what we would expect? So, for example, if we looked at the blue M&Ms, we could say something like, is the actual proportion of blue M&Ms 24%, or is it somehow different than 24%? Where mu again represents the true count of blue M&Ms. So then we would check some things like 0.24 times 60 and 1 minus 0.24 times 60. So we check the large counts, and then we check for is it a random sample, and we check for independence. We have those conditions, and then after doing that, we would go in. We would do a one proportion z-test where we would get a p-value of a z-value of negative 1.63 and a p-value of about 0.1026. And then if we went on this normal curve and we actually shaded that in, and we pull this highlighter up real quick so we could do something like this, we would have we have this inflection point. So this is about 1 deviation, so that would be about 2 deviations. So we would look here, and because it's a two-sided test, we would do likewise on the other side, so about 1.63 over here as well. And that total area that's been shaded at this point would be somewhere at approximately 0.1026. And so that's what we do. And again, just to justify that, believe it or not, this is my second take doing this video. So I had did this once before, but you just have to take my word for it. So what I want to do is we want to go and look at a stat test, one proportion z-test. And we can simply input the information that's needed. We have our null hypothesis, which says 0.24. All right. And then we have, out of 60 M&Ms, we have 9 that were blue. It's a not equal to. And then remember, we can actually calculate, and we can also have the calculator to draw our distribution, in this case of z-values, for us, so that we can see what the shading on the graph looks like. Once we do that, again, we get our z-value, we get our p-value, and then the decision that we would make because of the somewhat high p-value, with it being higher than 0.1, would also being higher than 0.05, we would say that we would fail to reject our null hypothesis, and that we do not have evidence that the proportion of blue M&Ms is somehow different than what it is that we would expect. All right, cool. So the next step, the next level in what we're looking at is, okay, well, we did that for blue, but what if we wanted to do that for the entire distribution, for all 6 colors at once? What is it that I would allow for us to do that? And yes, you guessed it, that would be our chi-square goodness of fit test. All right, so let's look at our chi-square goodness of fit test. Instead of looking at one color once again, we want to see how well an entire distribution fits this supposed model. And we're going to use our chi-square goodness of fit test to see if our entire bag of M&Ms follows a distribution as we expect. So with that being said, instead of just simply looking at a pi or a mu or what have you, we want to talk about the entire distribution of M&M. So when we set up our hypotheses, it's going to be a little bit different. For our null hypothesis, we're going to say something like the company stated color distribution is correct, or the proportion of colors is the same as what the company states. And then for our alternative, we will switch that up by saying something like the company stated color distribution is not correct. And another way to say that is at least two of the colors are disproportionate. All right. And again, to do this particular test, the type of test that we're going to do for this type of problem is going to be our chi-squared goodness of fit test. All right. And let's talk about the chi-squared distribution. It's a measure of how far the observed counts are away from the expected counts. And in general, our formula is chi-squared equals the sum of our observed minus our expected counts, quantity squared divided by our expected counts. All right. Chi-squared distributions are family density curves, only take non-negative values. Similar to the t-graph, a chi-square graph will differ depending on the degrees of freedom. If you have a 1-degree chi-square graph, that's going to be different than a 10-degree chi-square graph, which is different than a 15-degree of freedom chi-square graph, and so on. Now, some things that are similar with all chi-square graphs are still yet skewed to the right. All right. And then for the goodness of fit test, they're going to have C minus 1 degrees of freedom, where C in this case refers to the number of categories that we're looking at. All right. And so looking at this here, we have, I want to pause right here and let's go to our calculator and let's talk about how we can do some things in the calculator right here. So what I want to talk about, and let's move that out of the way. So what we have is, if we go to stat edit, notice what we've done already is we've taken a list, and for L1 we've put our observed counts, and then for L2 we have our expected proportions. Now I'm not actually ready to go and do what I need to do. Somebody may say, well, Mr. Sawyer, how do you know that we have 60? And we can simply add up all the numbers in L1 to get 60. So to get our expected counts, not expected proportions, we want expected counts. What we need to do is we need to take L2 and we need to multiply again by 60. And now, boom, we have our list of expected counts. All right. And with that, to get our chi-squared values, we can simply follow our formula once again, which says observed minus expected squared divided by expected. So what we're going to do is we're going to look here, and our expected counts we have in L1. We're going to subtract our expected counts, which are in L2, square that, and then divide by our expected counts again, which are in L2. And if we do that, we see that these numbers should indeed match what we have on our chart, and we see the actual subcomponent given for blue M&Ms, and we can do likewise for the remainder of these particular values. Now, just a couple of things I hope that we notice about these particular values. I specifically want to look at yellow. If you notice, yellow does the majority, yellow will affect our chi-square statistic, which will be the sum of all of these values. So even in our calculator, if we were to go second list, we can go to our math menu and actually add up all the values in a list. So if we add up all of these numbers here, what that gives us is our chi-square statistic that we will use in order to make our decision about whether or not we have any type of statistical significance. So for this particular chi-square test, we're going to have a test statistic of 10.18. All right, and we're going to talk about that in a second. We're going to talk about how to calculate that a particular value. But again, we cannot just skip to step 3. We've done step 1. We have not yet talked about our conditions, and so let me move that out of the way so we can jot this table down and make sure we have everything as was stated. Awesome. Now let's look at our conditions. Data must come from a random sample or a randomized experiment. That 10% rule still says population greater than 10 times the sample, and a large sample that all expected counts are at least 5. And we see that all 3 of those conditions are indeed met for this particular example. So with that being said, let's look at calculating the p-value. The combined chi-square value is 10.18, and again, we got that by simply adding up all the values, in this case in L3. All right, and then to find our p-value, we have, just like we have normal CDFs and we have TCDFs and all those things, we also have a chi-squared CDF. I'm going to show us a couple things real quick. We have a chi-squared CDF, and the syntax for chi-squared CDF is our lower bound, which in this case 10.18, our upper bound, which is infinity, E99, or if you just want to use a big number, we can do that as well, 1 bajillion or something like that. All right, and then the degrees of freedom. Remember, we had 6 categories, so we're going to have 5 degrees of freedom. So when we do that, we hit enter and we get a p-value of about 0.0703, something like that. Somewhere around 7%, 0.07. And that's the number, and I mistyped that. I apologize for that. That should be 0.0703 and not 0.703. So let me change that very quickly. I'm going to put a 0 right there, and we're going to act like that was always there. Or you don't have to act like it. You can call me out on my mistake. That's fine. And because our p-value is greater than 0.05, we fail to reject our null hypothesis. Again, this is at the 0.05 level. We will fail to reject the null hypothesis and say that there is not sufficient evidence. On the other hand, if we decided that we wanted to use a 10% significance level, then we would have significant evidence because our p-value is less than 10%, and then we would say that the color distribution is incorrect. So again, depending on what the significance, what the alpha level is, that will make a difference in the type of conclusion that we make. So if you notice that our chi-squared calculation is not really that difficult. Obviously, I show us a little bit in the calculator first, and I go and I show us a little bit more where the magic is. So what I want us to look at in the calculator is we're going to go back to stat test, and as long as we have one of the newer calculators, there is a chi-squared GOF test that we have in our calculator, and that's what we want to look at in order to do this chi-squared goodness of fit test. And simply all we need to put in to the chi-squared goodness of fit test is where our observed values are and where our expected values are, as well as the number of degrees of freedom, and then the calculator does all the dirty work for us. It'll calculate it, and it'll also draw it for us. So if you wanted to actually draw it, actually I want to go to calculate first, and I want to show you something. We get the chi-squared value and the p-value, also the degrees of freedom, and we have the CNTRB, which stands for contributors. And the contributors, what this is the individual chi-squared values for each category. And so basically what they do is they went in and they did observed minus expected squared, and they gave us all of these individual values so that we can see, hey, which one of these values affect the chi-square value the most. And that's going to be something that's important. If we see there's a significant difference, it may be that the entire distribution is off because a particular category is off, and in this case it was the 5 point what have you, which is what contributed the most. Excuse me, my words, but the 5.18, that's the color that contributed the most to our chi-square statistic. That's the color that was the most off from what we expected. All right, so that is the chi-square goodness of fit test. Hold tight, and then I'm going to give you all your assignment for today. What is up, happy people? We are back um, for our assignment tonight. I need you all to read section 13.1 in your text. What you will see is again the section on chi-square goodness of fit tests. And I want us to work those exercises at the end of section 13.1, not the ones through the middle of the section, but the ones at the end. I do apologize that I don't have those exact problem numbers in front of me right now. But if you can get those knocked out, that would be awesome. All right, so let's take the rest of the time in this class period in order to finish getting those problems taken care of. Thank you so much. And we will pick back up tomorrow with actual chi-square tests for two-way tables, where we're going to look at chi-square test of association, test of homogeneity, test for independence, which all are in essence the same thing. The calculations are the same, but the interpretation is slightly different. So that will be our discussion on tomorrow. You all have a good afternoon, and I guess that's it. All right.